Good morning, folks. Get things switched over to the dot cam here and we can get started. Oh, Qcam's already up. All right. How are we doing today? Did you guys have a nice long weekend? There we go. Okay. So today we're going to finish our little kind of introductory section by talking about section 2.6. But before we do that, I wanted to make sure we're comfy with everything from 2.5, the continuity material. And then if there's time, we'll start introducing the material that the syllabus has us on this week, which is just the idea of the derivative. So we're going to start talking about rates of change and whatnot. But like I said, before we get there, I want to make sure we're comfy with what we've done so far. So are there any questions from the homework that was originally going to be due on Monday, but was due today instead? Of course, if you need more time, I will extend it. But yeah, any questions lingering from this week's, or sorry, I should say last week's homework set? I haven't set exact dates for tests, but if you look here, I'll pull up the syllabus and then share my screen so everybody can see. What we have are test weeks, more or less. That way, as we get close to the time that would be appropriate for the test, we can pick the exact date that fits everybody's schedule the best. So right now, it looks like our first exam should be on the week June 8th to June 12th, somewhere around there. So that is week 5.
Hey, Professor, I have 3 questions of the homework.
Okay.
You don't have to do all 3, I mean, unless you don't want to, but 13, 16, and 24 were pretty difficult in my opinion. Maybe you can go over them real quick.
Yeah. Here, it looks like I got kicked out of WebAssign overnight. So let me sign myself back in. So 13, 16, and 29, you said? Are there any other homework problems that have been bothering you guys?
24, 13, 16, 24, and maybe 21, but okay. I don't want to be the only one asking for questions, so.
All right, don't feel bad. People are shy in this setting, especially as we're still getting to know each other. So being that person who's brave enough to break the ice and be the first person to start talking is a good thing. Please don't.
Awesome. Thank you.
So 13, 16, and 24. Let's take a quick peek here. Good, okay, 13, 16, 24. So 24, I'd be happy to go through all the way. If you look behind me, you'll see that we actually did 13 last week. That's the one that's still on the board behind me because that was the day that the doc cam wasn't working. So we can talk about.
I see.
Also, but and I'll do a quick maybe thing on 13 to show you the way to get started. So
awesome, thank you.
Screen share going here. Alrighty. So this was one of these lim h to 0 things, and we're going to be doing a lot of these. there's a little bit of random number generation in there. So you might not have an 8, you might have a 6, like in the statement of the problem on the board behind me. But in any case, the way we get started on this one, I'll answer those questions in just a second, is to rewrite these powers as fractions. So this is the same as the limit as h goes to 0 of 1 over 8 plus h minus 1/8, all divided by h, like this. And then to make progress from here, you would have to have a common denominator between the two fractions, subtract them. So what would that be? It's going to be 8 minus 8 plus h over 8 times 8 plus h. And then all of this is still being divided by h. Something like this. And then you'll distribute this negative, combine like terms, cancel anything that can cancel. I mean, I said I'm not going to do it, but we did these first few steps, and now we're close enough that we might as well finish it off. So this is minus h over 8 times 8 plus h. And then dividing by h is the same as multiplying by 1 over h. So you get this, and now you can cancel these guys. And so you end up with 1 over 8. So you got negative 1 over 8 times 8 plus 0, which is negative 1/64.
Got it. Thank you so much.
So the algebra steps here at the start, very important, right? Making sure that we interpret the negative first power correctly, and then knowing to have a common denominator. That's the whole game here.
Wait, what did you do on that third step? I'm so sorry. You multiplied by 8?
Here? Yeah, so this is me doing the common denominator step very quickly. So ignore the h downstairs for a minute. I just had a common denominator between the two fractions that I'm subtracting upstairs, and then subtracted them. And I did that in one step because I was trying to work this quickly. So my advice would be to go back and watch the video from, I think, last Wednesday, I think exactly 1 week ago, where we worked this out really slowly. But the step leaving here, what we did is I multiplied this little fraction by 8 over 8, and I multiplied this little fraction by 8 plus h over 8 plus h. And that gives them both the denominator 8 times 8 plus h, which is here. So the 8 over 8 contributes this, the 8 plus h over 8 plus h contributes this, and this is what we get. So come back here and have a common denominator. Okay. Any other questions on this one before we go?
No, sir.
Okay, I do see a question here about the study guides. So in the chat, the way the study guides work, I will give you guys some problems that I think are especially pertinent in preparation for the exam. And then you guys are going to write out nice, clean, careful solutions to those problems, and you're going to scan them and send them to me ahead of time. And we're going to talk about your solutions and make sure that your notation is okay, and that you're solving the problems in the way they need to be solved on the exam. So the study guide, you can think of it as just an extra homework set, but it's an extra homework set that you have to talk to me about before you hand it in. That's all. And the purpose is to get you ready for the test. I'll give it out a week before the exam. So 13 we wanted to look at. I remember 24 was one we wanted to look at. There were several in between that we wanted to look at also, right? Remind me those, please. 19 maybe? Was 19 one of them?
18.
18. So 18 is a good squeeze theorem problem. We haven't had a whole lot of practice with those, so I'd be happy to go over 18. I wonder if Lois knows calculus. I don't think a lot about the character development in Family Guy. I'm not sure if she went to college. She might know calculus. She might not be making that face. She might be down.
Probably not.
She's the only one of the Griffins I would expect to know it besides Stewie.
Oh, someone has that as a picture. I was like, what the hell are you talking about?
No, yeah, I see the stressed out Lois avatar there.
Yes, I see it now.
Okay, so here's the problem 18 from the homework, right? We want to evaluate this limit. What makes this limit hard?
Knowing what cos is and what to do with the squared. X.
So this piece, as x goes to 0, x squared goes to 0. That piece isn't too weird. But there is a piece here that's weird. I'm going to set the default to mute. If you'd like to speak, just go ahead and hold down your space bar. Think of it like a walkie-talkie button. So the thing that makes this weird is the 5 over x inside the cosine, right? As x goes to 0, 5 over x, that limit actually doesn't exist, right? 5 over x on its own. Let's do it like this. Look at that weird shit. As we get close to 0, this function is badly misbehaved, right? He's wobbling back and forth as fast as he possibly can. This rapid oscillation near 0 is because 5 over x goes to infinity as x goes to 0. And so the cosine of that thing is going to start wobbling back and forth really, really fast. So the problem is coming from this term, from the cosine of 5 over x term. And the way we can get around this, so this oscillates between -1 and +1 really fast near x equals 0. So we need the squeeze theorem. Right? I cannot, this cos of 5 over x is not continuous at 0. I can't just plug in 0 for x because 0 downstairs, right? 0 in the denominator, not okay. And the cosine of 5 over x wants to wobble back and forth between -1 and 1 really, really fast as I get closer and closer to 0. So from the graph of cos 5 over x, I still can't get this limit. I still can't figure this out. In other words, I can't do this with my limit laws. I can't say it's the limit of this times the limit of this. The limit of this piece is fine. He's 0, but the limit of this piece does not exist. He wobbles back and forth way too fast for that to happen. So I can't get there with my limit laws, and I can't get there by plugging in. So what I'm going to need to do is to make use of the only other tool I have right now, which is the squeeze theorem. Here's how we get started. That cosine piece, the problematic piece, is bounded between -1 and 1. That's an x. Which implies I'm multiplying through everywhere by x squared now in that inequality. And now I'm going to take the limit as x goes to 0 everywhere in this inequality. This is how we use the squeeze theorem. Remember, this is the kind of most natural way to do this. So now I say the limit as x goes to 0 of the thing on the right is less than or equal to the limit as x goes to 0, the thing in the middle is less than or equal to the limit as x goes to 0 of the thing on the right. Yeah, so I take limits everywhere in this inequality. We construct this inequality starting with the natural bounds for cos of 5 over x. This inequality, the starting one here, is true because it's true for the cosine of anything. No matter what you had inside your sine or cosine, it's always stuck between -1 and 1. So that's what those two trig functions do. And then from there to here, I multiply it everywhere by x squared. And from here to here, I take limits everywhere. A question was asked in chat, on the exam, will I indicate whether or not you need to use the squeeze theorem? Maybe. I don't want to give a more thorough answer than that. In the past, sometimes I have, and in the past, sometimes I haven't. It depends on how much of the problem revolves around your ability to recognize that the squeeze theorem is necessary. So I would say don't count on it, right? It's possible that I might, especially if it's something that's showing up in the context of another problem and I'm meaning for you to work through it quickly. But it is something that you need to be able to recognize. From here, though, the problem is pretty much done. If I take the limit on the left, the limit as x goes to 0 of -x squared is 0. The thing in the middle is the thing I want. And the thing on the right is also 0. Therefore, the thing I want is greater than or equal to 0 and less than or equal to 0. Therefore, the thing I want has to be 0 itself. All right. So this is a good example of a kind of classic squeeze theorem problem. Something like this definitely could show up on the exam. And I wouldn't be obligated to tell you that you need to use the squeeze theorem. I could say, just prove this limit is this thing, or calculate this limit, and then I would need to see all of the work that is here. So this is a fairly minimal solution. I don't think there are any steps that you could omit here besides the little sentence that I wrote up there, and still have a complete solution. Okay. The video from Friday has been posted. Yeah, I posted that yesterday morning. Sorry, it took me a while. I actually uploaded it and then forgot to post the link until yesterday morning. So that is up. So 18, 19, and 24 remain to be discussed. 18 is the one we just did. 19 and 24. Let's see. Oh, wait, no, 21. So 21 we actually did last week. I remember somebody asking about that. I am going to jump down to 24 now because I do want to make sure we spend enough time on the new material today. So if you have lingering questions from homework after lecture, I do have an office hour this afternoon from 1 to 2. So we will go ahead and discuss the discontinuity of this piecewise function. Now, I added some resources for you in Canvas. Under modules here for piecewise functions last Friday, I think. We get that there. Oh no, we got the graphing rational function stuff. Okay, so we haven't added the piecewise function stuff yet. So I remember we talked a little bit about piecewise functions, and it is the case that not everybody gets a good treatment of piecewise functions in their pre-calculus class. So I'm glad we're taking a look at this. Let me write this guy down, and then we'll come back to the dot cam and solve him. So he's x squared minus 3x over x squared minus 9 if x is different from 3. And he's equal to 1 if x is equal to 3. We want to discuss continuity at a equals 3. Okay. So when you see this big curly brace on the left like that, and you see some function like f of x equals big curly brace, and then some combination of different functions over here, what this means is f of x is the function who's defined by the rule x squared minus 3x over x squared minus 9, but only if the input you're feeding it satisfies this condition. So f of x looks like this if x is not equal to 3, and it looks like this if x is equal to 3. In other words, piecewise functions are how we kind of glue multiple functions together, right? If I want my function to be like a parabola from -infinity to 10, and then I want it to be like a straight line from 10 to positive infinity, I would make f of x equals this curly brace, the equation for that parabola, and here I would say x is less than or equal to 10, and then I would have my linear function here for x greater than 10. I made a note last time to find some piecewise function resources, but it looks like I haven't posted them, so I'll try to remember to do that for you today in case you haven't seen enough of this. They want us to discuss the continuity of f of x at a equals 3. And remember what it means to be continuous at a equals 3 is that the limit as x approaches 3 of f of x is equal to f of 3. So this is what we want to check for, which means that this limit has to exist, meaning the left and right limits have to be the same. This thing has to exist, meaning 3 has to be in the domain of f of x, and they have to be equal to each other. So there's kind of 3 different things that we need to check when we're asked, is this function continuous at this place? So first, we look at the limit as x approaches 3 from the left of f of x. Since the limit is interested not in what happens exactly at 3, not here, it's interested in what happens really, really nearby, but not equal to 3. That means we're looking at this sort of stuff, so we're going to be using this formula. So this will be the limit as x approaches 3 from the left of x squared minus 3x over x squared minus 9. Now, if I try to plug 3 in here, the bottom is 0, right? 3 squared is 9, so x squared minus 9 goes to 0 as x goes to 3, which means we're going to have to do some algebra. Remember, when you're doing this sort of stuff, you always need to write your lim. The notation really matters. Don't skip writing out the lim x to 3 minus. The numerator factors as x times x minus 3, and the denominator factors as x minus 3 times x plus 3. And now that we've factored everything top and bottom, we can cancel any shared factors. That's this guy. And we see that this is really the same as the limit as x goes to 3 minus x over x plus 3. And that function I can plug 3 into. When I plug 3 into that, I get 3 over 6, right? Or 1/2. Does everybody follow that limit calculation? So this is calculating the limit as x goes to 3 from the left of f of x. And there's a few important things here. First, recognizing that because we're talking about the limit as x goes to 3, I'm not interested in what happens exactly at 3, I'm interested in what happens nearby. So I'm going to use this formula and not this formula. That's kind of understanding what a piecewise function is and how limits work. So that gets us from here to here. And then in order to evaluate the limit, I recognize I need to get rid of the factor of x minus 3 downstairs, because that makes the bottom 0, right? If I try to plug 3 into something that has x minus 3 as a factor, that something will be 0. Since that something is the denominator, we need to find some way to get rid of it. And the trick that we've used every time we come up against something like this is to try and do some algebra, right? Here to factor the top and bottom and discover that there is a factor of x minus 3 that we can cancel. Having canceled that factor of x minus 3, I can go ahead and plug 3 into this expression in order to get the limit, and I get 3 over 6, which is 1/2. So that's the left limit. I need to see if that's the same as the right limit. And this is going to start out pretty much the same. I have the same issue. If I try to plug in 3, both the top and bottom are 0, so I factor top and bottom. And what we see is that the procedure here is really the same as the procedure for the left limit, which is good news. It means that the limit from the left and the limit from the right are likely to be the same. I cancel the x minus 3s. I'm left with the limit as x approaches 3 from the right of x over x plus 3. And I can go ahead and plug 3 in here and I get 1/2 again. Okay, so the left and right limits are the same, which means that the limit, the overall limit, does exist. It's 1/2. Right, we say that this limit exists because the left and right limits match, and its value is 1/2 because that is the matching value of the left and right limit. So from here, the last thing we need to check, remember we had those 3 little detailed statements about the definition of continuity. Left limit and right limit are equal to each other. And then we need to check that this is equal to the value of the function there. So is lim x approaches 3 of f of x equal to f of 3? Well, f of 3 exists. We know that because the function is indeed defined at 3. F of x is equal to 1 if x is equal to 3. So f of 3 is equal to 1, which is different from 1/2, which is the value of that limit. So no, the limit as x approaches 3 of f of x is not equal to f of 3. So this function is not continuous at 3. Even though the limit as x approaches 3 of f of x exists and f of 3 exists, because they aren't equal to each other, the function is not continuous there. In other words, what we have here is something like a graph with a little hole in it and then a little dot above or below that hole. I can show you what the graph of this function looks like. I think it'd be easiest to do in Desmos. So this function looks like x over x plus 3 if x is different from 3. because that's what x squared minus 3x over x squared minus 9 simplifies to. Maybe back in one more. All right, so I can type it exactly as it was without that factor canceled, and then you'll see the whole. Like that. So this guy actually has a hole right here at 3. Yeah. All right, everybody see that? And then instead of taking the value 1/2 there, our function has this point on it also, right? So this is your graph. It's hard to, there we go. So we've got this hole there, and then we've got that filled in dot above it. So that's how this thing is failing to be continuous. I'll do my best to reproduce this picture over here in a way that exaggerates what's going on. So x over x plus 3 otherwise. Yeah, okay. So we've got a vertical asymptote here. Here we've got a hole and it's at height 1/2. We're going through the origin. Okay, and then right here, we've got this, and this is at 3, 1. So this is what the graph of f of x looks like, at least to the right of -3. So the place they asked us to look, oh shit, all right, sorry. So this should be 3. I put the hole in the wrong spot there. This is what's going on with this function. There's a little hole there from the canceled factor top to bottom of x minus 3. And the way that the function is defined, that piecewise definition, instead of defining it to fill in the hole, which they could have done, if this piece right here was a 1/2 instead of a 1, then this function would be continuous because that would fill in this little hole. But because they chose to define the f of 3 to be 1, the hole is not filled in and the function is discontinuous. The value of the limit as x approaches 3 is 1/2. But f of 3 is equal to 1. And those two things aren't equal, right? The value of the function is not equal to the value of the limit. And that's what it means for a function to be continuous, for those two things to be equal. So this is the work that we need to show that. We'd have to calculate the left and right limit and deduce that those shared values are the value of the overall limit. And then we have to check if that's equal to the value of the function, which means you have to check if the function is defined there. It is. F of 3 is definitely defined. It's 1. But 1 is not equal to 1/2. So the function is not continuous. And that's the picture. Questions about this guy? I think this is one of the harder concepts to wrap your head all the way around, especially at the start of the course. So do make sure to take a look at those resources I posted in the Canvas modules if you're having a hard time with this. That's understandable. Both Patrick JMT and Paul's online notes have a lot of good stuff there. Patrick JMT has videos where he talks through lots of problems like this. And his explanations I find are really good. They're nice and clear and they're very concise. And then if you prefer to read for yourself and just look at written examples, the Paul's online notes has lots and lots of those. Anything else from the homework that we're dying to see? Turn this off real quick. I'm gonna look over 12 and 26 quickly. Okay. We'll do those fast. I did scrape those things out, right? So you don't have any of this stuff. Yeah, no. Okay, good. 12. So 12 is a multiply by the conjugate trick. We did look at a couple of these last week. I'll get you started on 12. And I'll do my best to hold back and not finish the whole thing. So what's the problem? If I plug in h equals 0, then the top and bottom are both 0, right? And in particular, the bottom being 0 is a problem. So in order to fix the issue, I need to somehow cancel a factor of h out of the denominator. And the way to get there for things like this is to multiply by the conjugate. So the conjugate of the numerator is what you get by taking that square root 1 plus h minus 1 and flipping this minus to a plus. So the conjugate here will be square root of 1 plus h plus 1. And if I'm going to multiply by that upstairs, I need to multiply by that downstairs as well. So really what I'm doing here is multiplying my function by the number 1. But it's 1 written in a very, very clever form. It's 1 written as the square root of 1 plus h plus 1 over the square root of 1 plus h plus 1. Because when I distribute, a lot of nice things will happen. So, we multiply fractions straight across, numerator times numerator, denominator times denominator. The denominator product here is simple. That's h times parentheses square root 1 plus h plus 1. The numerator product here is a little bit more complicated though. I'll have this square root times itself, so that'll just give me 1 plus h. Then I'll have minus 1 times the square root plus 1 times the square root. My inners and my outers eat each other up. And then my lasts are just minus 1. So you have to carefully FOIL the top. After multiplying by the conjugate. If you've ever seen how to divide complex numbers, it's the same trick. In fact, we get the name conjugate here from the concept of a complex conjugate in complex numbers. When you FOIL out the top, you'll have the square root times itself, which is just the inside of the square root. Square roots go away, right? Square root of 2 times square root of 2 is just 2. And then your outers and inners cancel each other perfectly. That's the idea of multiplying by the conjugate. We do this because we know the outers and inners will cancel perfectly. And then your lasts are just minus 1. So what you're left with here is the limit as h goes to 0 of h over h times the square root of 1 plus h plus 1. And I will let you take it from there. The factors of h will cancel, and then you can plug in 0 for h in the resulting expression. the multiply by the conjugate trick is a common enough one that I would not be surprised if you saw something like this on test 1 also. All right, so keep track of the common tricks. The tricks, there's a cute statement, I think Paul Hamish said it first, that if you use something once, it's a trick. If you use something twice, it's a lemma. If you use something 3 or more times, it's a theorem. We've used this twice now in class, maybe even 3 times. So I would expect this to be relevant moving forwards. I think that's everything that we want to touch on from the homework. The last few problems down here are very neat. So this piecewise function 1 and this piecewise function 1 are both good problems. I will take a look at the statistics and see how many folks were able to complete this, and maybe I'll extend this a little bit more. I am going to open up a new homework assignment for you guys today dealing with limits at infinity, section 2.6, which is the last little bit of material that, that we wanted to cover last week. And then if we have time, it would be nice to get into that this week, but given the holiday, we might not. Can I just see, using the React tools, give me a thumbs up or whatever if you were able to finish the homework before I look at the stats, just so I have some idea where to focus my attention in the lecture today. Okay, it's all right if you haven't, but if you're able to finish those, including those last 2, go ahead and show me. Okay, so a meaningful number of folks, but definitely not everybody. I am going to go ahead and teach you this last section here, this 2.6 section. That way, those of you who are ready to can get started on the new homework. So this is section 2.6. Which is on limits at infinity and horizontal asymptotes. So you may remember the definition of a horizontal asymptote involving some arrow notation. We say a function f of x has horizontal asymptote ASYMPTOTE, y equals L, provided as x goes to infinity, f of x goes to L, or as x goes to negative infinity, f of x goes to L. All right, this is the definition of horizontal asymptote that we use in college algebra and pre-calculus here at Santa Fe. And it's the one that Stuart uses. It's the common definition, the common notation. But in those classes, we didn't have any formal language for limits. So we just used these kind of arrows and we basically wave our hands. But the idea here is what you think it is that as x gets bigger and bigger and bigger, y gets closer and closer and closer to some particular number. And the picture is the one that you're familiar with. Maybe here's L. So here's the horizontal line y equals L. And a function having an asymptote like that there just means that the graph of the function settles down towards that line as you look further and further out. And we usually label it something like this. All right, so if the graph of the function settles down towards that line and gets closer and closer and closer to it, as you walk further and further and further out along the x-axis, then we say that that function has that horizontal asymptote. Right? This is our picture. You can cross horizontal asymptotes, remember. You can actually cross them as many times as you want. There are some functions that cross them infinitely many times. But the big thing is this settling down behavior, this getting closer and closer as you walk further and further out. And that's actually what your textbook gives as the intuitive definition of a limit at infinity. So really what we're going to say here in section 2.6 is that limits at infinity are the same thing as horizontal asymptotes. And we will define the limit at infinity in terms of that, or in the same way that we define horizontal asymptotes. I want to use the precise phrasing that they use. Yeah, so the intuitive definition, we'll give a few, but it's the intuitive one that you'll use most of the time. This is the intuitive definition. We say that the limit as x goes to infinity of f of x equals L if we can make, or if we can get f of x as close as we want, or as close as you want to L by taking x to be really big. That's the idea. So if f of x gets closer and closer to L as x gets bigger and bigger and bigger, that means we should be able to make f of x as close to L as you want by taking x to be sufficiently large. This is kind of a way of trying to soften the delta epsilon language from section 2.4. Of course, we don't cover section 2.4, but what we're saying here is that the limit as x goes to infinity of f of x equals L if, as you go further and further and further to the right, the graph of f of x gets closer and closer and closer to the horizontal line y equals L. In particular, if you were to give me some amount of closeness that you wanted, I could find some x such that if you look to the right of that x, your f of x, your y values, will be within that amount of closeness. So the words we use here are like arbitrarily close, or as close as you want. Your textbook does have one or two other definitions here. Means that these can be made arbitrarily close to L by requiring x to be sufficiently large and negative. But they don't actually give a formal definition. No, okay. Yeah, so this is okay. The only difference between the definition at plus infinity and the definition at minus infinity is you replace really big and positive with really big and negative. Really, the nice way to say this is to link it up with horizontal asymptotes. So the thing we were defining here was the limit at infinity. Say the line y equals L is a horizontal asymptote for f of x if at least one of lim x goes to plus infinity f of x equals L, or lim x goes to negative infinity f of x equals L is true. All right, so this is the nicer way to think of it. Limits at infinity are just horizontal asymptotes. If your graph settles down on its horizontal asymptote as you walk out to the right, then that horizontal asymptote is the limit as x goes to plus infinity for your function. If the graph of your function settles down on its horizontal asymptote as you go to the left, then we say that that is the limit as x goes to negative infinity of f of x. Questions about the definition of a limit at infinity or this picture? So here I would say that the limit as x goes to infinity of f of x is equal to L, because this function is settling down on its horizontal asymptote as we go out to the right. Or in other words, as you put in bigger and bigger and bigger x values, the y values, which remember are f of x, get closer and closer and closer to L. Right? So it's very much like the definition of a limit at a regular number, right? We would say as x gets closer and closer and closer to a, does f of x get closer and closer and closer to L? And that's how we would define a regular limit, a limit that's not at infinity. A limit defined at infinity is the same sort of thing, except it's hard to get closer and closer and closer to infinity. You have to think about what it means to get closer and closer and closer to infinity. And really what it means is that x gets really fucking big. So if as x gets really fucking big, f of x gets really fucking close to L, then the limit as x goes to infinity of f of x equals L. And it's the same thing as saying you have a horizontal asymptote. Okay, so this might take a few seconds to digest all the way. Try to see it in the context of your previous math classes where you talk about horizontal asymptotes. And I think that will serve you really well. We can look at some examples. Let's jump straight to the arctan example. I think I would like to look at one or two more beforehand. If I want to look at the limit as x goes to infinity of 1 over x, I should ask myself, oh, come on, camera. You can do it. Damn it. Come on. There we go. Ah, come on. This thing's having a hard time focusing. All right. If I want to look at the limit as x goes to plus infinity of 1 over x, I should ask myself, along the graph of 1 over x, what happens as my x values get bigger and bigger and bigger and bigger? The graph of 1 over x is one I know well, and you should know well also. It looks like this over there, and like this over here, having this horizontal asymptote, y equals 0. So as we walk out really, really far to the right along this graph, what are my y values getting closer and closer to?
You said closer to positive infinity?
So as I send x to positive infinity, what are the y values? What is 1 over x doing?
0.
Yeah, it's going to 0, right? Because we have that horizontal asymptote, y equals 0. It also happens to be true that if you look at the limit as x goes to negative infinity of 1 over x, if I walk out really, really far to the left, then my y values are approaching 0 as well. So finding limits at plus or minus infinity is really the same as finding horizontal asymptotes. And you have lots of tricks for that from your last 2 algebra classes. Where did my chat go? In fact, one of our first theorems
is going to 0 too. So
yeah, exactly. If R is a positive number, any positive real number, then the limit as x goes to infinity of 1 over x to the r is equal to 0. This is an important theorem, and we should recognize why this is true. You can think of it as a consequence of that rule from your algebra class, that if the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is y equals 0. Well, here the bottom power is a positive number, and upstairs that's a degree 0 function, degree 0 polynomial. And it turns out to work just fine, even if r isn't a whole number. So this doesn't just work in the case where you're talking about rational functions. This also this works well if you're talking about any power function where the power is negative, or 1 over any positive power. Also, limit x to negative infinity 1 over x to the r will be 0. As long as the function is defined for negative values. That is, if r is a number like 1/2, then I can't plug in negative numbers here, so that function wouldn't be defined. But for any number r such that that function is defined for negative inputs, you can be guaranteed that the limit at plus and minus infinity will be 0 if you're just looking at 1 over x to the r. So this is a useful thing. We're going to use it a lot. And I'm going to show you a bunch of examples where we make use of that. But before we do that, I've got one more example where we want to work from the graph. Maybe I'll give a quick sketch of the proof. As x gets bigger and bigger, x to the r gets bigger and bigger. Thus, 1 over x to the r is the reciprocal of bigger and bigger numbers as x goes to infinity, and the reciprocal of a big number is always close to 0. That doesn't look like a 0. 0. All right, this is the basic idea here. So reciprocal of a huge number is a small number, right? Like the reciprocal of a million is 0.000001, very, very close to 0. So as x gets bigger and bigger, any positive power of x will get bigger and bigger, which means that the reciprocal of that thing will get smaller and smaller as x goes to infinity. The reciprocal of a big number, like x to the r, if x is big, is small. And as x gets bigger and bigger, that reciprocal will get smaller and smaller, i.e. will get closer and closer and closer to 0. So the limit as x goes to plus or minus infinity of 1 over x to the r is 0. Don't sweat the proof too much. The proof should be digestible to you at this point. This is definitely not a rigorous proof. It's just kind of the idea behind it. A rigorous proof here would require work with deltas and epsilons. And that's not the sort of thing that we do in the non-honors version of this class. But if you'd like to see the delta epsilon arguments, come to me in office hours. I'd be happy to show them to you. They're not that bad. The next example I wanted to look at is to find the limit as x goes to plus infinity of the inverse tangent function and the limit as x goes to minus infinity of the inverse tangent function. Okay, so for this guy, I'll divide the last bit of my page into two pieces here. We'll do one on the left. The limit as x goes to plus infinity of the inverse tangent of x. This is one that we're going to get straight from the graph. So you got to know the graph of arctan. Does anybody know what the graph of the inverse tangent function looks like? So I guess the most convenient way for me to do this is with Desmos. Here he is. This is the graph of arctan. It kind of looks like the cube root graph. It's the same sort of shape as the cube root graph, only instead of going up to infinity and down to negative infinity, he's bounded. He's bounded between these two numbers. And if you're wondering why he's bounded between those two numbers, we should go back to your trig class notes and make sure you understand how the inverse tangent function is defined. Basically, we took the graph of the regular tangent function and threw away everything except for the bit between negative pi over 2 and pi over 2. We trashed all that stuff. And then we inverted what was left inside. When you invert what was left inside, you get this. All right, this is what he looks like. So if we imagine walking further and further and further to the right along the graph of this red function, are my y values getting closer and closer and closer to something? We see it as I walk further. Yeah, they're getting closer and closer and closer to that green line. So what is the limit as x approaches positive infinity of the inverse tangent of x? What is this limit?
Pi over 2.
Yeah, exactly. Why? Because as x gets bigger and bigger, the inverse tangent of x gets closer and closer to pi over 2. And we're seeing this from the graph. What about going in the other direction? What is the limit as x goes to negative infinity of the inverse tangent of x?
Negative pi over 2.
Yeah, beautiful. If we look over here, as I go further and further and further along the red out to the left, my y values are getting closer and closer and closer to this bottom green asymptote. And that guy is negative pi over 2. So this guy is negative pi over 2 because as x gets more and more negative, the inverse tangent of x gets closer and closer to negative pi over 2. And again, this is coming from the graph. Okay, so these are two very important limits. I guess you could say three very important limits, right? 1 over x raised to any positive power will go to 0 as x goes to plus or minus infinity. And the inverse tangent function goes to pi over 2 as x goes to plus infinity, and negative pi over 2 as x goes to negative infinity. Given those two things, we can actually calculate quite a lot. This is also how we prove that rule involving the degrees of rational functions, top and bottom. So you remember that rule that you learned in college algebra about the degree of the top versus the degree of the bottom, calculating horizontal asymptotes. That is all a consequence of this theorem. And we're going to be able to prove that rule. But before we go there, I just want to give us some practice calculating these things. And maybe the easiest way to do that is to try and sort of combine those two at once. So let's do this. Using just what we have, meaning no tricks from outside this class, just that theorem and the definitions we have. Let's find the limit as x goes to positive infinity of 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. We know from stuff we've learned in other classes what this limit should be. The degree of the top is 2, the degree of the bottom is 2, so we're going to take the ratio of lead coefficients, that's 3 over 5. That should be our horizontal asymptote, and because horizontal asymptotes and limits at infinity are the same thing, this limit should come out to 3 over 5. But let's pretend like we didn't have that trick, because that trick isn't rigorous at all. And what we have now are theorems, those are rigorous. So how would we approach this otherwise?
Factor.
If plugging in the number I'm trying to take the limit as made the top and bottom 0, then I would definitely need to factor upstairs and downstairs. But that's not the case. Both of those things, the top and the bottom here, as x goes to infinity, they both go to infinity. Those are both parabolas opening up, right? So as you walk out along those graphs to the right, both of them go up to infinity. So it's not the 0 over 0 problem we need to deal with here, it's the infinity over infinity problem. The main idea is to try and make something like this try and make something like what I have my theorem about here show up. And the trick to doing that, the trick to making stuff that looks like this show up, is to divide top and bottom by the largest power of x you see anywhere. This is a trick that's going to come back in Calc 2 when you talk about limits of sequences. So what I'm going to do here is I'm going to multiply by 1 over x squared, top and bottom. I'm going to divide the top and the bottom by x squared. So I look for the largest power of x showing up anywhere in my original function, and I divide the top and bottom by that. When I do that, I get the limit as x goes to infinity. I'm going to distribute this 1 over x squared across the top. 3x squared times 1 over x squared is 3. minus x times 1 over x squared is minus 1 over x. And minus 2 times 1 over x squared is minus 2 over x squared. And downstairs, I do the same thing. I'm going to distribute that power. Or I'm sorry, I'm going to distribute this 1 over x squared. 1 over x squared times 5x squared, that's 5. 1 over x squared times 4x, that's plus 4 over x. And plus 1 over x, plus 1 times 1 over x squared is plus 1 over x squared. So this is what we get. And I distribute those top and bottom. And now I can use my limit laws. I can take the limit of each of those pieces on their own. So here's what I get. I get the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 1 over x minus, I'm going to pop the 2 out, limit as x goes to infinity of 1 over x squared, all divided by the limit as x goes to infinity of 5, plus I'm going to pop the 4 out, limit as x goes to infinity of 1 over x, plus limit as x goes to infinity of 1 over x squared. So first I divide top and bottom by the largest power of x. That means I'm dividing top and bottom by x squared, which is the same as multiplying by 1 over x squared. However you want to think about it is fine. This thing is what you get if you take the original thing and divide everybody by x squared. That's how we get to here. And then from here to here, I just gave the limit to each of the pieces on their own. Three is a constant function. The limit as x goes to infinity of 3 is 3 minus, what is this limit? What is the limit as x goes to infinity of 1 over x?
0.
0, right? That was the first example we did. The limit as x goes to infinity of 1 over x is 0. In fact, the limit as x goes to infinity of 1 over any positive power of x is 0. Then we have minus 2 times the limit as x goes to infinity of 1 over x squared. That's also 0 by our theorem. Downstairs here, the limit as x goes to infinity of 5, that's 5. 5 is a constant function. Plus 4 times the limit as x goes to infinity of 1 over x. Well, that's 4 times 0. Because the limit as x goes to infinity of 1 over x here, this is 0. Plus the limit as x goes to infinity of 1 over x squared, that's also 0. So we end up with 3 minus 0 minus 2 times 0 over 5 plus 4 times 0 plus 0. That's just 3 over 5. So this came out how we expected it to. And if you think very carefully about what we did here, you will be able to see why that trick you learned in your algebra classes works, because you could always do this. You could do this with any rational function. You can divide top and bottom by the largest degree, the largest power of x, and then send x to infinity and just treat each little piece on its own. The largest degree term will yield a constant function when you divide out by that largest power of x. And everything else will be like 1 over x to some power. And each of those things, 1 over x to some power, will go to 0. So the lower order terms, like this x term and this minus 2, they didn't contribute anything to the limit. The only thing that really contributed from the top was the 3x squared. Similarly, the 4x down here and the plus 1, they didn't contribute anything. The only thing that really contributed anything was the 5x squared. Because when we divided top and bottom by x squared, we got constants and then shit that goes to 0. Constant and then shit that goes to 0. So that's where that trick you learned in your algebra classes comes from. It comes from this theorem. questions on this example? Of all the stuff we're doing in 2.6, this is probably the most crucial example to understand because this is the fundamental idea that will come back. Meeting controls, yeah. No, the overall limit here definitely does exist. It's 3/5, 3/5. Yeah, we get 3 plus some 0 stuff divided by 5 plus some 0 stuff. So the limit as x goes to infinity of that function is 3/5. All right, so the original limit is equal to this. This is equal to this. And this is equal to 3 plus a bunch of 0 stuff divided by 5 plus a bunch of 0 stuff, which is 3/5. Yep. If the top was 3x cubed, we would divide top and bottom by x cubed, or multiply top and bottom by 1/x cubed. Exactly. Other questions on this example? Okay, so at its heart, this is the same as the college algebra problem, like find for me the horizontal asymptote. And since we have tricks that work really well for these things that we know from previous algebra classes, I'd like to show you how we can extend. Yeah, it is. It's nice. It's good stuff. That trick you learned in college algebra, comparing the degree of the top to the degree of the bottom, that only works if the functions you're dealing with are rational functions, meaning a ratio of polynomials, right? So the powers of x had to be whole number powers, couldn't have any weird square roots or things like that floating around. This theorem, however, can get us to stuff that trick could never touch. So the next example I want to work for you here is one that we couldn't have done before. Doing on time. We're getting there. So let me do this one more example. I know we're right up against the edge of the clock here, but if you'll bear with me, it'll be good. It's worth doing this now. So I want to find the limit as x goes to infinity of the square root of 2x squared plus 1, all divided by x. First important thing, a mistake I see a lot, the square root of 2x squared plus 1 is definitely not equal to the square root of 2 times x plus 1 or anything like that. You can't distribute the square root, right? You cannot give the square root to the 2x squared and the 1 separately. Doesn't work like that. That shit never works. It's just incorrect algebra. Can't be done. What we can do here, though, is play this same trick where I divide top and bottom by something. Now, upstairs, I have an x squared and it's under a square root, and that's going to want to grow at the same speed as x on its own, because the square root of x squared is x. It's just that I can't distribute that. I can't give the square root to the 2x squared and the 1 separately. But I notice that I'm going to try dividing top and bottom by x. So the fastest growing term upstairs is an x squared, but it's under a square root. So it's going to behave more or less like x. And the fastest growing term downstairs is definitely just x, because that's all that there is downstairs. So the limit as x approaches infinity of the square root of 2x squared plus 1 over x looks like this if I divide top and bottom by x. Now downstairs, 1 over x times x, that's easy, that's just 1. But upstairs, I'm going to do something a little bit sneaky. I'm going to write this as the square root of 2x squared plus 1. But then the 1 over x, I'm going to write as the square root of 1 over x squared. So I need to write the 1 over x as the square root of something so that I can combine the two pieces. And the something which works is 1 over x squared. The square root of 1 over x squared is 1 over x. And it's actually 1 over the absolute value of x, but it's close enough. Since we're sending x to plus infinity here, the absolute value thing wouldn't be an issue. So if we wanted to take the limit as x goes to negative infinity of this, that might be a good first example for our next class. But I just want to show you this trick now, because it is such a nice trick. The bottom is just 1. I'm going to forget about the bottom. Upstairs here, I'm going to rewrite this as a single square root with the product of those two things inside. Like this. All right, so the square root of a times the square root of b is the square root of a times b. So the square root of this times the square root of this is one big square root with this times this underneath. Now I can distribute. Two x squared times 1 over x squared is 2. And 1 times 1 over x squared is 1 over x squared. And now by my limit laws, I can take the limit inside the square root. And the limit as x goes to infinity of 1 over x squared is 0. So I get out of this the square root of 2 plus 0, because this piece right here goes to 0 as x goes to infinity. So we get out of this the square root of 2. Next time, I'm going to look at the limit as x goes to negative infinity of this thing. And I'd like you to think about how that would go differently. So the only difference there is that 1 over x is not the same as the square root of 1 over x squared if x is negative, because the square root of 1 over x squared is really 1 over the absolute value of x. You might remember this distinction of the square root of x squared not necessarily being x, but being the absolute value of x from a previous algebra class. So we're going to have to handle it just a tiny, tiny bit differently. And I bet if you think about it, you'll be able to find the differences. So I encourage you to try that. This is where we're going to have to cut it for today, because I do have another class that starts in a little bit. If you would like to talk with me about any more of these things, or if you need more time on homework 2, I totally understand. Please go into WebAssign and submit an extension request. And I will go through and clear all those extension requests today during my office hours. So please go ahead and do that if you need it. And then watch a little bit later today, I will open up the next homework, which will be on tangents and rates of change. So we're getting close to our first really big thing here, the derivative. That is the largest chunk of stuff in Calc 1, has to do with rates of change, derivatives, slopes, and we're very, very close to being ready to talk about those things. So if you need more time on homework 2, please get in there, submit the extension request, and watch for homework 3 to open up a little later today. No, I haven't. I'm still trying to figure out what to do with this extra office hour business. So because as far as I can tell, there's only 2 people in all of my classes who can't make the regular office hour. If you are one of those people and you haven't been accounted for, please send me a Canvas message. It might be the case that I'll just leave the 3 and then schedule office hours for those people as needed. So if you can't make our regular office hour, feel free to just send me a Canvas message asking to schedule an office hour as needed. I know that that kind of sucks though, so I am still working on it. It's just that the 2 people who had conflicts with the existing office hour schedule also have conflicts with each other. So there's no single hour I could add that would work for both of them. And so I'm just not sure what the most efficient way to solve that problem is yet. But for now, we're definitely going to keep the Monday, Wednesday, Friday 1 to 2s. And if I'm able to find a way to efficiently add more office hours that will be helpful for the people who need them, I will. But for now, if you need to talk to me about problems, or if you want to talk to me about problems and you can't make it to a regular office hour, just send me a Canvas message and we'll set up an office hour for you. We'll do them one at a time like that, at least for now. Any other last minute questions? Okay, so I'm going to go ahead and end the meeting. You don't have to worry about typing the here thing in there anymore. I'm not taking attendance every day. But if you have any questions, come by the office hour later. If you can't come by the office hour later, please contact me via Canvas and we will schedule a special office hour meeting. It's not a big deal. It's not a hassle at all. Please don't feel bad about doing it. And that is it. Otherwise, I'll see you guys on Friday.